Hi everybody, my name is Matt Smith, and this is the first video in hopefully a series of videos that I'm making about nutrition, about all the things I've learned over the past couple of years, really diving in deep, trying to learn everything I possibly can about this topic. And I've learned a lot. It's been an amazing journey, and I can't believe how much I thought I knew, but it turns out I did not. And I guess that also applies for society. There's a lot of stuff we think we know, which turns to not be correct, as far as I can tell. So I want to get into that because it's important that we eat kind of what our bodies are designed to eat and use our bodies the way they were meant to be used. And so this is my first video in trying to explain what it is I've learned along those lines. Okay, so of course I got to say this at the beginning. No, I am not a doctor, which is actually a good thing, as we'll find out. A lot of doctors, unfortunately, don't have a lot of nutritional training. Some admit maybe less than a day in their entire, 8 years or whatever it is of medical training. It's really not their fault. This is sort of the way they're supposed to be. They're supposed to treat the person that comes in the door, not really prevent the disease, 10 years from now. It's really not exactly what they're for. So I hold nothing against them. But anyway, no, I'm not a doctor. I am an engineer, though. And this is interesting because I am finding a lot of engineers in this field now, because this is interesting. You can take measurements, you can measure all these different things and see how testing and changing one variable changes the rest and so forth. So engineers eat this data up, or eat this field up, because, so to speak, because they love to graph all these things and see trends. And so I guess I'm in a lot of good company here. This is probably the most important sentence of the entire presentation. I am seeing everywhere I go that there are biases in studies and reports and papers and stuff that are very clear in some cases, not so clear in others. There's a lot of money out there when it comes to food production. And so there's a lot of money being spent to make us think one thing or other things. And I'm not really a big time believer of all these conspiracies and so forth, but it's hard to ignore some of this stuff. But anyway, the only bias I can really think of that I have is, if anything, I don't want to hurt animals. So if I'm presented with data that can go either way, I may sort of lean, I'll be honest, a little bit towards the side of the animals. Unfortunately, if we do see that animals in some aspects are helpful for our diet, I'm going to put that out there, and then we can decide what to do with that later. But at least be honest with what the truth really is. And let's see. Oh, and also sort of related to that is, I don't have any financial stake in any of the videos or any of this nutrition information at all. I don't sell anything related to it. I make industrial equipment that has nothing to do with food or any of this stuff. So you can take, at least you can know that I have no axe to grind here. Why did I get interested in this in the first place? Well, this is a chart of my mother's CA125 enzyme. What is that? Well, that is, unfortunately, if you know what that is, it's basically a marker for ovarian cancer. You can see back in 2015, pretty low. But then it started, then she was up with some symptoms. She came in to be examined, and they looked at this enzyme again, and sure enough, it was way high. And this is the cancer taking over. And you can see she had surgery, had some of her organs removed, and then it started chemotherapy here at the green line, which did an amazing job. I'm very impressed with chemotherapy drugs. But unfortunately, the way chemotherapy works is it can often kill all the cancer cells, but very commonly, especially in late stage, which my mom was, she was late stage 3, you can often kill the cells, or most of the cellular cells, cancer cells, but there might be some that are still resistant to the chemotherapy drugs, or can hide in places and then come back out when the chemotherapy ends. And that's kind of what seemed to have occurred. You can see we went from 13.8 as a marker all the way up to 22, but we started a diet kind of on the uptrend here, which seems to possibly, it's up for interpretation. There's no 100% proof of anything here, but you can see that it's that something turned the corner here, and that the momentum began to come back down. So maybe that had to do something with the diet, who knows. But this is the reason I got interested in this first place. So when I first heard that my mom had ovarian cancer, I was researching, looking up doctors, of course, as everyone does, or the articles and so forth. And I ran into a doctor, Dr. Barbara, I forget her last name, but she was doing a study on ovarian cancer patients and diet, and specifically the ketogenic diet. And I was curious, what does this all mean? I emailed her and I said, hey, is there anything that you can tell me about what you found out so far? And you can see from her email here that that she was still in the beginnings of it, but she recommended I read this book called Tripping Over the Truth. So I did. I grabbed a copy of that, written by Travis Christofferson, and this is an amazing book. If anyone is interested in cancer, I think this book is probably the most, it gets technical, and a lot of it forced me to go back and do like Khan Academy and stuff to learn about organic chemistry and some other basic organic stuff. But this really has some interesting thoughts about cancer and ways that we can combat it or prevent it in the first place. Spoiler alert, it has to do a lot with carbohydrate, and so I was reading other books after that about what happens when you minimize your carbohydrate intake. So Jeff Volek and Stephen Finney are very famous doctors in the field. They've written a couple books about living with this diet, as well as what happens to sports. If you're into sports, how does low carb affect it? Does it make it better, worse, nothing at all? And then some other common books when you talk about diet and nutrition that are common. These are all best, as you can see, best New York Times bestsellers, and these are very entertaining as well and very informative. But I also spent a lot of time watching doctors on YouTube. Here's some thumbnails of some of the videos I was watching. And all different fields: endocrinologists, pathologists, cardiologists even, and oncologists and nutritionists, and so forth. Here's some more that I was watching, and to give you an idea, and learned a lot of interesting things. So let's start at the beginning. Macronutrients is a term that you hear a lot in the world of nutrition, and it just means kind of a source of energy. It's a block of food, a type of food that supplies the body with energy. So carbohydrates is one type of group of macronutrient. Also is proteins. We can get energy out of proteins. And finally, fats. All three groups here contain energy. And so the question is, generally speaking, what does our body generally burn? Well, of course, it matters what you feed it, but the average American has something like this, where right when they eat, they're going to be burning. If you have roughly the same amounts of these three macronutrients, you're going to be burning carbs at a pretty high rate, and fat somewhere down there, and protein fairly minimal. And in fact, protein, generally speaking, is minimal enough that I'm kind of going to round it down to 0 for our purposes of discussion, although it certainly is part of it. Protein, which is composed of amino acids, has a place in the discussion, but carbohydrates and fat are the more interesting of it and what we'll be dealing with the most. This is just a quick little graph, though. On a high-carb diet, people's ability to burn fat, grams per minute in this case, is fairly low. But if you're on a low-carb diet, meaning you're probably going to eat more fat, you'll notice that the rate of what you burn of the fat oxidation or fat burning goes up. And you can see we're almost 3x in difference. So the body adapts to what kind of diet that you're having. If you eat more fat and fewer carbs, you'll have higher fat burning and so forth. That's just a neat little graph I found I thought I'd include. All right, so let's talk about carbs. We all know they taste good, but what are they really? Well, if you break down carbs, they're interesting. They're molecules only composed of carbon, which are gray in these pictures, oxygen, which is red, and hydrogen, which is white. And they're ring structures at their heart. You can see a ring of 6 over here for glucose, and our fructose has a ring of 5. Galactose, we're back to a ring of 6. And then we have oxygens and hydrogens hanging off. These are what we call simple sugars. Another term is monosaccharide, mono meaning one, and saccharide meaning sugar. Galactose is not as common in the discussion. Glucose and fructose play the biggest roles in our diet, so I'm going to be talking about them the most. But what's interesting is that you can bond these simple sugars together. So for example, this graph shows the same thing, but this is kind of the organic chemistry way of showing these same molecules. Here's the ring of 6, and you'll notice they don't even bother putting carbons anymore, because carbons are so common in organic chemistry that you're just going to be drawing a lot of C's, as well as the H's, the hydrogens that will hang off. So those are kind of ignored. Just the other not as simple like hydroxylide molecules and other things hanging off are shown instead. But this is just the same thing as what you saw in 3D, the previous slide. Okay, so where does glucose come from? Well, we all probably know this. It comes from plants. We take carbon dioxide, we take some water, and some energy in the form of sunlight, and all these CO's and H's combine to make sugar, and then this is glucose, and some oxygen too, which is nice because we can use the oxygen to burn the sugar later. So anyway, it comes from the sun. The sun rearranges is the energy used to rearrange these molecules to become glucose. So when you fly over the Midwest or whatever and you see a lot of agriculture, this is what we're doing in scale. We're taking the sun and using it to create glucose and fructose. That's also in plants as well. More fruits generally, as the name implies. But when I see this, I often think of solar cells. It's sort of the same idea, isn't it? We're taking energy from the sun and we're storing it in electrically or chemically, perhaps. Very similar, all from the sun. Okay, so plants can make it, as we just saw, but even animals can make, in this case, glucose. There's a process called gluconeogenesis, so new gluco creation. And this is I'm not going to go into the details of it right here, but generally we take amino acids and it goes through this process to become the glucose molecule. And this process is regulated by a hormone in our body called glucagon. You may have heard of insulin. Well, glucagon is also a hormone that is pretty important. So if you have low blood sugar and we need to make some glucose, then glucagon will be released into the body to get some glucose made. By the way, this is interesting because of the 3 macronutrients, there are some fats that you have to eat. They're called essential because your body can't make them from other components. Likewise, there are some amino acids that are essential. You have to eat them somehow, from somewhere, because they can't be made from anything else. But carbohydrate, or glucose, can be made easily by the liver, so it's not actually considered essential. So that's one of the things I often see a lot from nutritionists that really don't know exactly what they're talking about, because they say you have to have carbs. Well, yes and no. Our body does rely a little bit on glucose, but that small amount that it needs can actually be delivered via the liver through this process, instead of having to eat the carbs or the glucose, eat it exogenously. So, okay. Now, simple sugars, in this case a glucose and a fructose, can be bonded together. Notice there's a circle around the hydroxyl or the OH molecule here, and just the hydrogen of this hydroxyl over here, and that's 2 H's and an O, which is known as H2O. You can rip that off, and so a water molecule goes away, and this oxygen stays behind. And an oxygen likes to have 2 bonds, so it has one left and one right. And so what we've actually done is we've done a glycosidic bond. This is also called a dehydration reaction because we're taking water out. And we've taken 2 monosaccharides and we've created one di meaning 2, disaccharide. So if you take a glucose and a fructose and you bond it together like this, you've actually made a disaccharide called sucrose, which is, we all know and love, that is what table sugar looks like. So here is sucrose, which again is the glucose and a fructose bonded together. Now if you take galactose, another simple sugar, and glucose bonded together, you can get lactose. So that's what I'm showing here, common in milk or dairy products, obviously. Okay, well, these different sugars have different sweetnesses to our tongue. So if you use sucrose, our table sugar, as 1.0, glucose is a little less sweet, fructose is a little more sweet, and then you can see lactose, as you'd guess, is not very sweet at all. But notice how sweet some of these artificial sweeteners can get. That's pretty incredible. So you don't have to use as much of that in like a recipe or whatever as you would sucrose. So anyway. Here's what's interesting, though. You can not just stop at a disaccharide. You can make trisaccharide or after a while they get tired of naming them, I guess. They just call them polysaccharides, meaning there's a lot strung together. So starches are very easy. They're just a bunch of glucoses bonded together. Nothing very exciting there. And starches are essentially what a lot of plants like to make. They make starch, and that's basically their form of storing fat, although they don't make fat. This is their form of storing energy that they might burn at a later date, unless we harvest them and then we eat them instead. Now, interestingly enough, they also can do something different. Well, they'll take a glucose, as you can see up here, same thing, or it's close, and then you bond it to another glucose that is flipped over, and then bond it to another one that's flipped over again. So we're alternating up, down, up, down. And what we have now is something called cellulose, which is actually stronger. And so plants make a lot of cellulose in order to be as a structural component, and that's what they make their skin and what everything out of. Interestingly, we don't have the ability to break these bonds. We can break the bonds of starch. We have enzymes in our gut that can break these bonds and turn starches back into simple glucose, simple sugars, which means that eating starch, like from a potato, even though it doesn't taste sweet at all, is essentially like eating a bunch of glucose, a bunch of sugar, which is a lot of people just can't wrap their head around, but unfortunately it's true. Cellulose, though, we can't break these bonds, so it just ends up going right through us without us being able to really get at these simple sugars that just come out the other end. And fiber is, or dietary fiber is another term for this chain. Finally, these two are generally made by plants. However, animals, humans as well, can take these glucoses and also make strands of them. We do that to store the glucose as well. So here's a glucose, here's another one, but then we have we kind of flip a little bit, and then we go for a while as a regular starch again, and we flip again. And we have this strange pattern. So whatever reason, I don't know why we do it this way, but this is what it looks like when we store sugar, and that's called glycogen. And so we have some of that in our liver and some of this in our muscles. I think we'll get to that soon in the next slides. But anyway, going back to simple sugars, fructose and glucose, it's you can see that honey, for example, is mostly fructose, so a little sweeter. Sugar is half and half, right? Because it's one atom of each, or one molecule of each bonded together. But notice now, when you start talking about the juices, the apple juice concentrate and pear juice and the nectars and stuff, you're getting a lot of fructose in there. And they do that because, or these are used then, concentrated juices are used by manufacturers to really bring out the sweetness. So if you look at the back of a naked juice, everyone's probably seen one of these, here's what the label looks like. Notice what the first few ingredients. Again, ingredients are listed in order of what's the most in there. So there's the most apple juice, then second is mango, and then pineapple, then banana, then kiwi, and these are all fructose. So we have enormous amounts of fructose sugar inside this, and then of course at some point we got broccoli and spinach, but who knows? I mean, the ratio for this to that is probably pretty low. And indeed, if you look at the total carbohydrate at 33 grams, most of it is sugar. Incidentally, if you take, and none of it's fiber, interestingly, so there's no cellulose, no fiber in this drink. But the total carbs is 33 and the sugars are 28. That means the remainder, 5, is just a regular carbohydrate, like a starch or something like that. Sugars are essentially the fructose and the glucose by themselves, or as a disaccharide. Okay, so let's talk about the body now. The body stores, as far as storing carbohydrate. So the blood that we have in our body stores a little bit of glucose, a little bit of sugar in it. You've all heard the term blood sugar. There's definitely some sugar in your blood. Even if you don't eat sugar at all, even if you have a zero-carb diet, your liver will still make glucose through that gluconeogenesis thing we discussed to get this roughly up to 25 grams or a couple hundred. I've seen as high as 200 calories of glucose in the blood, which is not very much. It's about like 3 or 4 teaspoons of glucose in your entire blood volume, so not a lot. In your muscles, you'll have a lot more, so roughly 13, I've seen 1,500 calories, somewhere in that ballpark, and the liver stores some as well. And I should say that this is not glucose. This is the chain form that we store. And there's a reason we do that I'll get to in another video. Basically, glucose is a little dangerous. If you have high blood sugar, sugar attacks things, and we'll get into that later. But if you string them up like glycogen, they become neutralized in terms of they don't really attack things anymore, which is great. So, but look at the pie chart. You can see most of the glucose, carbohydrate in our body, is in the muscles of your body. That's so when you use your muscles and you use up some of the fuel in the cells, it has glycogen right there to break down into glucose to resupply very quickly. The liver holds on to some to put into the blood when the blood sugar is low, and then there's whatever's in the blood at the time. So that's kind of the look at it. But look at the total, roughly 2,000 calories. So not much storage of carbohydrate in the body. And no matter how much pasta or how much sugar you eat, and we'll talk about what happens then, if you're only storing 2,000 calories, what happens to the rest? Well, before we go there, we're going to be talking about fat. But before we talk about fat, I want to show you this interesting molecule. Pretty simple, just a carbon with 4 hydrogens around it. And you can see a 3D there. This is what we call methane. And interesting, and so it's just hydrogen and carbons. What we can do is, or what nature can do, is they can take this carbon and maybe string a couple more together. And so, like if you have 2 together and then hydrogens all the way around, ethane, and then 3 gives you propane, and then there's butane, and then finally octane, what we put in our cars. And it's only just a string of carbons with hydrogens all the way around. And I find this interesting. Well, actually, let me go a little further. What happens if we burn the simplest form, methane? Well, there's our CH4. We add some oxygen and a little bit of energy to get the reaction started. Maybe it's a spark of a match or something like that. Just a little bit to start the process. And then carbon dioxide and water is released and a lot of energy. And where does the energy actually come from? I never really knew this. It turns out that the bonds between the hydrogen and the carbons are actually very weak, meaning that it doesn't take much, just a little bit of energy to break those bonds and create new bonds between the hydrogens and the oxygen, and those new bonds are stronger, so the tendency to want to get from left to right is very strong, and that's really what the energy is. So breaking the bonds between the hydrogen bonds there is where the energy is. And then photosynthesis rewinds the process. Okay. Well, let's talk about fat. This may look a little more familiar now. Here's our long chain of carbons and hydrogens going all the way around. So very similar to what we saw in the methane and the octane and all that. But the big difference is we have this thing on the left. We have an oxygen and an OH over here. And they call that a carboxyl group. Why? I don't care. I don't know. But they kind of call this the beginning, or the alpha end of the fatty acid. And then we have the omega being the last letter in the Greek alphabet, so this is the end. So every fatty acid really has this structure where you have a backbone of carbon, a bunch of hydrogens going all the way around. And so what you can do is say, well, there's a carboxyl group in red, so there we have COOH, and then we have the end group, CH3, so there it is over there, and then some number of the backbone structure, the CH2, and then N. And N can change. There's actually a lot of different fatty acids. This particular one, stearic acid, has an 18 carbon backbone, but you can have 16, and they give them names because why not, I guess. And some of these fatty acids are very helpful, some not so helpful, but our body can actually use these very similarly to the way a car burns octane. All the energy in these hydrogens is ready for us to pluck and use for our engine if we want to burn fat. Now, let's take that same fatty acid. I guess this is a little shorter, but who cares? It's the same idea. Carbons with hydrogens all the way around. It can happen that maybe 2 consecutive hydrogens next to each other are ripped off, and that'll make these carbons kind of angry because they want to have these 4 bonds. So what they'll do to make up for the fact that they've lost a neighbor is that they'll have a double bond, and what you can see here is the equal sign between these 2 carbons. So again, 1, 2, 3, 4. So this carbon's happy, and likewise we have 4 here. The thing is, though, these hydrogens will repel each other, so you have a kink. So this happens with fatty acids. And here's a complicated fatty acid, again using that the thing where you don't draw the carbons at every corner, but they're there, and you can see some double bonds in here between the carbons, and the hydrogens are off on all ends. And you can see that even though it's drawn straight in this form, in reality you have an interesting kind of curve, all these different kinks in the fatty acid. So we really basically have three types of fatty acids. We have one where there's no kink at all. There's no double bonds on the carbon here on the backbone. There's one where we have one double bond, and there's one where you can actually have multiple double bonds. You can have several, like we saw on the previous slide. So this is called saturated fat because there is no more places to stick hydrogen. There's no double bonds on the backbone that we could break that would allow us to add more hydrogen. This is a saturated fatty acid. And because they're straight like this, generally not kinked, they can stack really well at room temperature. So they tend to be solid at room temperature. So whether it's butter or tallow or, God, what are the other ones that you hear a lot of? Things like that. Let's just leave it. Saturated fatty acids, that's what they look like. Now, if they have one kink, they can still somewhat stack a little bit, but generally they're going to be liquid. And so this is monounsaturated because there's only one double bond, so mono. And there's monounsaturated fatty acid, often abbreviated as MUFAs. So olive oils, coconut oils, things like that are very high in monounsaturated fatty acids. And then finally, polyunsaturated fatty acids, where you have more than one double bond. So you got a lot of kinks all over the place. You're going to definitely be a liquid. And so corn oil and all those oils, vegetable oils, which is ironic. I don't know why they call them vegetable, because they don't come from vegetables. They come from seeds or corn or soybean or whatever, but not vegetables. This is what it looks like for that. Okay. Well, different foods have different amounts of each type of fat there. The saturated, the mono, and the polyunsaturated. You can see, for example, olive oil has a lot of monounsaturated fatty acids in it. And the dairy products seem to have a lot of saturated fat. Meats can have a reasonable amount of saturated and mono, and not so much polyunsaturated, at least for the type of, especially beef. Beef is really low on polyunsaturated. You start to get some with the turkeys and the leaner meats. And finally, nuts. You can see that the almonds have a lot of monounsaturated, cashews, macadamians, obviously known as a fatty nut, mostly monounsaturated. But look what happens when you start talking about walnuts and sunflower seeds. You're starting to get a lot more of the polyunsaturated. So one quick word though. So again, we have the saturated fatty acid, but if you do have a situation where you have a kink like this, and the hydrogens are on the same side, that's called a cis double bond. It is possible to somehow flip this hydrogen over to the other side, which is what you see here, and they're no longer cis formation. This is called a trans fat. So what's interesting is the polyunsaturated oils, that like cottonseed oil, for example, was very popular in the early 20th century. And then I think it was Procter & Gamble figured out a way to take this fatty acid, this oil, which is fatty acids, polyunsaturated, and cause this to happen, to actually move the hydrogen to the other side, which kind of straightens it out a little bit. So you turn a liquid into a solid, and that's where Crisco got started. Crisco stands for crystallized cottonseed oil. And what's also interesting is Procter & Gamble then used a lot of the money they made from this to start the American Heart Association, which we'll start getting into when we talk about biases later. But they made a lot of money on this product because what happens is trans fats, turns out they are delicious. They make very nice flaky pastries and crackers and cookies and you name it. Trans fats were awesome. Unfortunately, they kill you. That's the one negative, is that they're very unhealthy for you. And that's not really a point that's contended anymore. In fact, it's to the point now where most countries ban trans fats over a certain amount to try to keep their population from getting too sick. Okay, one last thing. Here is a fatty, as far as fatty acids are concerned, here's a fatty acid here, here's a second and a third, and we also have in this slide another molecule over here called glycerol, which is pretty simple, just 3 carbons with hydrogens most of the way around, almost like a fatty acid itself, but it's got 3 OHs or 3 hydroxyl components on it. And again, you can see we can circle the OH on one and the hydrogen on the other hydroxyl and rip out 3 waters, which will cause this oxygen to be double bonded. And we've actually bonded 3 different fatty acids to this glycerol. This is generally how fats move around the body in this formation. There's 3 of them, so they call it, and there's glycerol involved, so this is called a triglyceride. And so triglyceride is really a name for, is another way of saying mobile fat, or fat on the move, let's say. Although it is stored that way too. In our fat cells, it's stored in triglyceride form. Okay, so we talked about how many carbs are stored in the body, roughly 2,000 calories. I've graphed that for us here, male and female. Notice how many calories we store in fat form around the body. And of course, I just took the average. I did a quick calculation. I took the average weight of a man and a woman and the average fat content or fat percentage, and multiplied it out and got a large number of calories. So a lot of people don't really know this, that this is the case, that our body stores very few calories in carb form, at least when you compare it to fat. To me, the example that often comes to mind is a tanker truck, where we're walking around with a giant tank of energy, and there is another tank down here that is sort of like what I consider the carbs. And most people walk around only drawing from this tank. And that's part of what this nutrition talk is all about. How do we start to burn this and not just the carb tank? Okay. Oh, you know what? I think it's interesting to just pursue this just a little bit further. If you do the math on like how many calories you need for a 26.2 mile and the average calories per, body weight and whatever. Here's an average body weight, 185. That's me. And you need roughly 3,000 calories plus or minus. But our body doesn't store that much calories in carb form. So if you're a body that generally just burns carbs, which most people are, you're not going to even be able to get through a whole marathon without having to eat. And if you don't eat, the racers call it bonking, where you run out of energy and you just basically collapse. So you're going to need, there's a huge market of sugary materials to get carbs into your body during the race so that you can keep going. And books were written about how do you get as much carb into your body right before the race so you can offset this a little bit and not have to eat as much during the race. But it's interesting because carb burners definitely need to eat during the race because, again, they're using that small tank, and that tank will be empty before they finish the race. So this is something that concerns them. In contrast, the guy that set the record for the American 100 miles, which is an amazing 7-minute mile for every 100 miles he did, he is a ketogenic diet advocate, and he actually doesn't have to eat anything during the race. He just eats his fat that he already has eaten before. Let's put it in a delicate way. So he actually set the record on a ketogenic diet with no carbs. And most people will say that's impossible, that you have to have carbs to run. There's no other way around it. Well, we're seeing a lot more examples now of ultra athletes that are showing that fat actually might be the better way to go. And there's some other benefits besides fat storage that might come up, and we'll talk about that. Okay, so now let's talk about, we've talked about fat, we've talked about carbohydrate, and we know we eat these things, but we not really talk about what happens next. Well, there's a molecule in the body called ATP, adenosine triphosphate. And I've broken it up in a picture here, but really all you got to know is that there's this little group on the end, a phosphate group. There's 3 phosphates, but the last one is the one that gets knocked off a lot, and there's a lot of energy in this bond. When this group is removed, a lot of energy is released, and that energy is used by the body to do a lot of things, whether it's to flex muscle fibers so you can move, or it's to transport nutrients around the body, or to cause chemical reactions to occur, or building polymers like proteins, like RNA, for example, is built using ATP. ATP is a ridiculously important molecule for all animals. And the whole point of eating, at least as far as energy is concerned, is to get this thing recharged. So when this phosphate group is knocked off, Our metabolism's sole purpose is to put that right back on there so we can use it again. We recycle this molecule over and over and over again. I heard in one podcast that we use roughly our body weight in ATP each day. So these molecules are used over and over and over and over again the same day. So generally speaking, if we have ATP, this is the same molecule again, and when we actually convert it to ADP, so we only have two phosphate groups, we knock a phosphate group off, and then the metabolism is to put it back on again. So it's a constant circle, a recycling circle to get that done. So how is ATP recharged? By the way, I kind of think of it as a loaded gun. This is the gun up here, it's fired and it's spent down here, and then we reload the gun. Okay. So how do we make ATP? Well, here's our three groups of macronutrients, and there's different processes that we use for each macronutrient. Protein is mixed because some of the amino acids in protein kind of take the route of the sugar route, if you will, and others take the fat route. But essentially what happens is, depending on the type of food we're talking about, we'll have a different process that essentially results with a molecule called acetyl-CoA, or coenzyme A. And it also, along the way, will have made a couple ATP as well. So we already made some energy. This acetyl-CoA is then fed in to the Krebs cycle, or sometimes called the citric acid cycle, which I'm not going to go into detail. All you got to know is a couple more ATP are made, but also some interesting molecules, NADH and FADH2, are made or essentially recharged. And those are then fed into a process called the electron transport chain, which makes enormous amounts of ATP. And both the Krebs cycle and the electron transport chain are done in the mitochondria of the cell, which is this crazy looking thing here. The first process is done outside the mitochondria. Incidentally, I'll do a little hint here. Cancer cells, many of them have broken mitochondria, so they really can't do these two cycles. All they can do actually is the glycolysis part. They can't even do lipolysis. So they essentially depend on sugar to make their ATP, and then they do a lot of glycolysis in order to supply themselves. So they're very inefficient, which is a good thing, but that requires them to get a lot of sugar. And I'll say one other thing. One way you know if you have cancer is you can take sugar, glucose, and you can radio tag it so you can see it on a machine, on a scanner. You eat a lot of it, wait a minute or two, or for it to distribute through the body, and you scan for the radiation. Where did that sugar go? And if you have cancer, the cancer will have grabbed a lot of it, and you'll see a lot of the tagged radiation in that area. That's called a PET scan. So we use this point that sugar is used by cancer in order to find it in the first place. Where is the cancer in your body? Well, that's how they find it. Okay, that's all I got for part one. This is just laying the groundwork for the basics of the metabolism and the basic, how carbs and fats, what are they made of. Part two, I'm going to get into what happens when you eat sugar, and then also what happens when you eat fat, and what are the positives and negatives, and we'll take it from there. See you next time.